Welcome to my talk about the spectral Hermite approximation of the Boltzmann collision operator. My name is Andrea Hanke and I would like to present you the results that me and my supervisor Manuel Torrior developed in the past years of my PhD thesis. I'm going to start by discussing non-equilibrium gas flows and why we need the Boltzmann equation to approximate them accurately. Then I will show the spectral Hermite ansatz. Then I will proceed with results from Wang and Chai, and then I'm going to talk about the ansatz that Manuel and I developed, which is the irreducible spectral Hermite ansatz. I will show the implementation of the irreducible spectral Hermite ansatz and talk about a numerical example. I will conclude my talk with future tasks and a summary and outlook. What are non-equilibrium gas flows? Equilibrium in a gas is maintained by a sufficient number of particle collisions within a reference volume. The equilibrium is not present in case of too few collisions in relation to the observation scale. This can happen either when you are dealing with rarefied gases or when you're dealing on very small scales. And this leads to the applications of the methods that you can develop for non-equilibrium gas flows. These include things like atmospheric entry flows on Earth, Mars, or Titan. We can also have things like vacuum machines and micro-electromechanical systems which deal with a small scale of the non-equilibrium gas flow. We can describe this by simplifying everything and just considering a three-dimensional single-component monatomic ideal gas, and then we can define the Knudsen number as a non-dimensional scaling parameter. The Knudsen number measures how rarefied the gas is or how small the observation scale is. Depending on the regime of the Knudsen number and the experimental setup, different approximations are valid for calculating the gas flow. On the one hand, you have Knudsen numbers which are very small, and for these, the Navier-Stokes-Fourier equations are absolutely fine to use as an approximation. And then you can have very large Knudsen numbers, and this is the kinetic regime where you can enter with equations that describe free flight of the atoms, essentially. And then here we have this transition regime, which is the play field for the Boltzmann equation. Here, the Navier-Stokes-Fourier equations are not sufficient anymore to describe what happens accurately, and we're also not yet in the kinetic regime. The distribution function gives the time-dependent position and velocity distribution of particles. So f of x, t, and c gives the number density of particles that are within a certain velocity and position frame. And then the evolution equation that describes how this distribution function changes within time and space, developed by Boltzmann already in 1872. And it basically just says, well, changes of the distribution in time must either come from free molecular transport or from collisions between particles within the gas themselves. And this collision operator describes the physics between the binary collision of two particles. And the focus for today is indeed this collision operator S and how we can approximate it. So first of all, we're going to simplify the Boltzmann equation to a space homogeneous case. We make our distribution function position independent. So this just gives a time-dependent velocity distribution of particles. We end up with the space homogeneous Boltzmann equation where the evolution of the distribution function in time is only given by the collision of the particles within the gas. There have already been many results developed, for example, based on the spectral Fourier approach, which Paresky and Russo started to discuss since 1989, and also Gamba and Thakur-Bouchanam. There are also, for the bilinear collision operator, existing results and implementation by Wang and Chai, which is a fairly recent development. Let us compare the spectral Fourier approach and the spectral Hermite ansatz. In the Fourier approach, you need a finite cutoff in the velocity space, whereas in the Hermite ansatz, you can deal with the infinite velocity domain. Fourier approach is linear and relatively difficult to adapt to velocity and temperature, whereas the Hermite approach is nonlinear and physically adapted to velocity and temperature. The transport operator enters in the Fourier approach as a convolution, and in the Hermite approximation, the transport operator is almost diagonal. One of the huge advantages of the Fourier approach is that the fast Fourier transform is actually available, whereas something similar like a fast Hermite transform for the general distribution function is unclear whether that's even possible or not. Another advantage of the Fourier approach considers the matrices, which are less hard to compute in contrast to the Hermite ansatz, where the matrices are quite hard to compute. And then the nonlinear collision operator for the Fourier approach has been available for a relatively long time, and for the Hermite approach, the nonlinear collision operator and its implementation is first of all computationally expensive, and second of all a fairly new development. The Fourier approach uses the standard L2 space, whereas the Hermite ansatz uses the weighted L2 space. Let us take a look at the spectral Hermite ansatz. It has been introduced by Grad already in 1949. You shift your velocity coordinate system in such a way that the medium velocity is 0, and then you approximate the distribution function as an element of a polynomial space of maximal degree n, multiplied by a Maxwellian function. So if you want to take a look at our distribution function f of t and velocity c, we have a time-dependent polynomial in C, which is of degree n or less. And we also multiply the whole polynomial by a global Maxwellian function, which is just a Gaussian-like equilibrium distribution. As mentioned before, we need to use a weighted scalar product. We expand our approximation space with the orthonormal basis set. For that, you use the Hermite polynomials, which are orthonormal with respect to exactly the scalar product. And then you have an expression for your distribution function as sum over all weights and all basis functions multiplied by the Maxwellian. So then you can simply project the Boltzmann equation, and this gives you a linear system of equations, which you can solve typically numerically. This is exactly what Huang and Chai did in their paper from 2019, and they found that calculating the collision operator, which looks relatively innocent here, is actually quite complex. It involves an 8-dimensional integral, but it was actually possible for them to calculate it as analytically as possible. And they also implemented everything, so you could say it's problem solved, right? Well, storing this collision tensor is increasingly demanding with higher n. Of course, Wang and Chai knew that. They also gave rough estimates for a generic potential. If we set our maximal polynomial degree n to 10, then 0.2 gigabytes of data that you would need to store. Whereas when you just double n to 20, you're already in the neighborhood of 40 gigabytes. They knew that, and they developed a relatively clever workaround involving linear approximation for moments of higher orders. However, they still found that evaluating this tensor vector-vector product is increasingly time-consuming, even with their workaround. As an example, for the Maxwellian potential, they measured for a polynomial degree up of 10 that one evaluation of our collision operator takes about 37 milliseconds. For n equal 20, they didn't even give the measured time, but from the paper you can roughly extrapolate in which order of magnitude you are, and they probably took about 8 seconds. Of course, you could ask the question, do we even need a large n? I mean, if we set n equal to 10, the numbers are not too bad, right? You could manage with them. Let us look at a numerical example. The BKW solution of the Boltzmann equation. It uses the Maxwell potential to describe the interaction between our atoms in the gas. I just took the expression for the analytical solution again from Wang and Chai's paper. And the important part is you realize, of course, f is dependent on t and c, but it only depends on the magnitude of c, right? Wherever c enters, it enters as a magnitude. You can visualize the initial function as something like a 3D donut. It is rotationally invariant. F only depends on the magnitude of c. So we can plot our initial distribution as a function of exactly the magnitude of c. And what we can see is the exact solution here. This is the blue curve. And when we set our maximum polynomial degree to 10, then we can approximate our distribution functions relatively well, but with n equal 20, we are really on the mark. And the point, of course, is this is still a relatively nice distribution to approximate. When you want to work with something like a discontinuous distribution, you really need a high order of polynomials in order to approximate them. So is this the end of the story? I mean, okay, we need a high degree of n, and unfortunately that gives us a fairly large amount of data and also a fairly long evaluation time. Well, no. We actually developed and implemented a better method. For our method, the storage estimate for a generic potential with n equal to 20 is in the order of 42 megabytes compared to 40 gigabytes. Also, the evaluation time measured for a Maxwellian potential is 5 milliseconds, which is of course much better than the estimated 8 seconds. Of course, now the question is, how do we do that? And the answer is we use the spectral Hermite ansatz, but we use a different basis set. Our orthonormal basis is based on the irreducible subspaces of our polynomial approximation space. And because of that, we decided to call our ansatz the irreducible spectral Hermite ansatz. We use an expansion based on spherical harmonics and Laguerre polynomials. Our basis functions C alpha now are basis functions depending on 3 indices, A for the radial index, N for the angular index, and L to describe which one of the spherical harmonics you want. They are orthonormal with respect to the weighted scalar product, and the important part is they are adapted to the decomposition of Pn of our polynomial space into its irreducible subspaces. We are not the first to work with this very particular basis set. Kumar developed an analytical solution to the bilinear collision operator in 1966, and Gamba and Ryazanov also developed first numerical results exactly for this very particular basis set. Let us discuss what is so special about this very particular ansatz. The collision tensor, of course, now consists of different entries because we have a different basis set. We can also write our indices alpha, beta, gamma as triple indices as described before. And now we can use representation theory. And representation theory implies the decomposition of the collision tensor into an S tensor and a Q tensor. Let me start with Q. Q deals with the coupling of the 3 spherical harmonic basis functions. It needs to be computed only once. It's a purely mathematical operator. It's related to the Clebsch-Gordon coefficients, and it's 0 for most combinations of our indices N and L. S, on the other hand, is the physical parameter that encodes the particle collision. As you can see, it's invariant of the angular indices L, and these S coefficients are the only degrees of freedom for the collision operator. So already with this overview, we can explain how we are so much better than the other approach. Setting n equal to 20 and using a generic potential, we can compare the actual versus the perceived degrees of freedom. So if you look at the collision tensor in the basis given just by the Hermite polynomials, you will end up with somewhere around 2.7 times 10 to the power of 9 degrees of freedom that you would expect that collision operator to have. However, the actual degrees of freedom are given by S. And for S, we can approximate something around 1.4 times 10 to the power 5. So already we have much fewer coefficients that we need to store for S than for the full C. Of course, that's not the full story, because we also need to store our Q. It has a storage size of somewhere around 38 megabytes. This, of course, is also related to the performance. Our coefficients S times Q is 0 unless the triple of n's meet very specific conditions here. Additionally, our Q is very sparse. If you look at all the entries in Q for all possible n's, then we have less than 5% non-zero entries. And thirdly, we developed an optimized implementation of our tensor-vector product. And I'm going to show you how we did that. So the task is to implement the multiplication and sum over all these coefficients here. We start by giving each triple of n's a unique case number. Let's call it Q. And then we save the expansion coefficients, which really just form a vector, in a very specific order. We group them by the L index. When we look anywhere in the vector, we can find a position P, which depends on A and N, and that points to the beginning of a section of our W vector, where we have some value of A, some value of N, and then the L runs from -n all the way up to n, so that these two n plus 1 coefficients are grouped together in these vectors that I called Vn. And next step is to hardcode for our triple of n's, which we identified by Q, the following operation. Vnl, which is the resulting vector, is equal to some coefficient, some constant alpha, multiplied by the sum of the Q, which acts on the two input vectors v and v. We next give our code an input list. This input list has the coefficients s, the unique index number q, encoding our triple n, and the three positions p. And then in the calculation of our C++ code, you just go through each line of this input list, apply equation 11, given with the pointers p, a, b, and c, and we of course now set our placeholder alpha to the corresponding s coefficient. This has the following advantages. Our code is fast, and it requires relatively little memory space, as you have seen already. It is easily adaptable to different potentials. Furthermore, we can apply two kinds of reduction of computational effort. On the one hand, we can use representation theoretical reduction of computational effort. This is done by choosing a problem-specific subspace of our polynomial space, and that leads to even more s coefficients having to be 0, in the sense that we can just kick them out of our list that we put into our calculation here. The other reduction is a numerical kind, which is relatively easy to explain. You choose just some epsilon, relatively small number, and only compute those terms with s being bigger than epsilon. The disadvantages of our implementation are a relatively long compilation time and a relatively large program memory-wise. The main challenge that we face is computing the physical collision of parameters s. Let's first look at the numerical reduction of the computational effort. You can see here the number of q's that are non-zero plotted against the unique case number q. When q is small, we only have very few non-zero entries, and as q goes larger, in principle you can see a larger amount of entries, but you can also see some of the cases they are very easy to compute and other cases are very hard to compute, in the sense that you have a lot of coefficients in the sum here that you need to evaluate. You can see here a table of the computational effort of Q, which is color-coded in red. The redder, the higher the effort for our calculation Q. And also in blue colors, we can see the magnitude of our S coefficients, also depending on Q. And because we have multiple combinations of ABC for the same index Q of our N triple, you have many entries of S that apply to the same Q. And let's zoom in a little bit, and then we can see what I mean by numerically reducing the computational effort. All the dark blue squares, for example here, they show a high value of our physical parameter S. Whereas all the light colors, they show a fairly small number of S. For example, here we have a fairly red column, and in this red column we can see there are a few coefficients of S, but they are fairly small. So now the idea is, let's get rid of all the small values of S, and from this plot we can already hope that this can indeed reduce the computational effort of our overall evaluation by quite a lot. Now let's go to computing our physical parameters S. Just like with Wang and Chai, what I've written here as, a fairly innocent looking fraction actually involves an 8-dimensional integral, which is quite complex to solve and also computationally expensive to solve. And similarly to Wang and Chai, we were able to give an analytical solution as a function of angular integrals. We can solve 6 dimensions of the 8-dimensional integral and end up with an expression that only involves the angular integrals, which make up the remaining 2 dimensions of the full integral. These IFK depend on the potential, and in general you need to solve them numerically. One of my goals is to simplify this overall integral S as much as possible without knowing the potential, so without having a solution for the angular integrals. And the idea is that this will give me a generic expression for our S coefficients, and then if we want to calculate S for a given potential, we should end up with a much faster computation of S, because we already solved 6 dimensions of this 8-dimensional integral. What we already were able to do, because it's much less expensive, is calculate our S coefficients for the Maxwellian potential, since the overall collision tensor coefficients are 0, unless a relation between the output and the input indices holds. This is true for Wang and Chai, and this is also true for me. So we could use this Maxwell potential and apply it to the numerical example from the beginning to calculate our solution. This Wang and Chai also did this, so this is a very nice test case to compare our results. And because we chose a basis that is able to represent angular and radial dependency, we know that all our coefficients W must be 0 unless N and L are equal to 0. Because, again, this initial function is rotationally invariant. Setting the maximal degree of our polynomials to 20, we only have 11 relevant coefficients, so we can just list them. This also plays into the representation theoretical reduction of our approximation space. With this setting, we only look at a very small subspace of our polynomial space, which is the subspace of rotationally invariant polynomials. The only relevant coefficients of S are those where all n's in the triple are equal to 0, which leads us to only 34 S coefficients. Measuring the evaluation time of this setup gives us less than 2 microseconds. So we've gone, by using representation theory, from 8 seconds to less than 2 microseconds. Let's see how this method holds up. First, we can see here, starting from t equal to 0, our BKW solution goes closer and closer to the Maxwellian distribution. This should also be reflected in the evolution of the expansion coefficients. Let's take a look at them. What we see here is the evolution of the expansion coefficients of the analytical solution. On the top, W of A equal to 0. Then we can see A equal to 1, and then we start from 10 going all the way down to 2. We first note that for A equal to 0, we only get a straight line. This is as expected because the case A equal to 0 actually corresponds to the density, and the BKW solution is one where the density does not change. Similarly, for A equal to 1, this expansion coefficient is related to energy conservation, and we do want A equal to 1 to be 0 for all the time. Okay. So let's look at the remaining coefficients, which actually do change in time, and compare them to the numerical solution. We can see all of these coefficients tend to 0 with increasing t. This is exactly what we want, since with t going larger and larger, our distribution function tends more and more towards the Maxwellian distribution, which corresponds to the case A equal to 0 is 1, and all other coefficients are 0. Secondly, we can observe that the analytical solution given by a line and the numerical solution given by dots exactly correspond to each other. This leads me to the future tasks. We are computing the generic expressions for our physical collision parameters S, and with them we then want to compute more test cases with different potentials. For example, hard spheres potential, hard power potential, you name it, we would like to compute them. We also want to compare computational time and accuracy for different values of epsilon to see, hopefully, that we can decrease computational time without losing too much accuracy. Let me summarize what I've talked about. We used bases consisting of spherical harmonics and Laguerre polynomials instead of Hermitian basis functions, and with those, we're able to use representation theory to decompose the collision tensor C into two components S and Q. We found a large amount of sparsity both in S and in Q, and implemented an efficient evaluation of the bilinear collision operator based on this sparsity. Our implementation is roughly 1,000 times faster and 1,000 times less memory intensive than the current state of the art. As a first numerical example, we calculated the BKW solution and found that the analytical solution is in agreement with our numerical approximation. Next steps are more numerical applications with more potentials, for which we need to compute the generic collision operator, and we want to do some timing tests to further optimize the calculation with epsilon. Here are the references that I used for today's talk, and I would like to acknowledge the financial support from the Deutsche Forschungsgemeinschaft through the IRTG grant. I'm very glad that I'm able to pursue this work. Thank you for your attention. I'm looking forward to your questions in the conference.